Okay, now let's go back to the second part of the tutorial for the assignment number 4. And you can now check the module and, sorry, the canvas, and you will find the module for the assignment number 4 is available for you. Uh, this is the previous video I made, and this is the slide, the sheet for the questions. And here I added a calculator for the parameters, so you don't have to get any mistakes while you do your calculation for the parameters. Actually, this will cut more than half of the time for the calculation because you are going to focus on doing the using of the equation rather than doing the calculation of the parameters. And sorry if I hadn't actually supplied similar calculator in the previous assignment. Now we'll start to have a look on this slide and this PDF file here, the same one I showed you in the previous tutorial. We only have one question. Once again, the P is the first number, the R is the two last numbers, and the Q is the last three numbers. You don't have to do too much. You just go to the parameter calculator and you're going to key in the numbers here. I use the 989 and 789 because that's what we have in the example I gave you for the numbers. And when you change these numbers, for example, again to make it, for example, the 5, 3, 5, 4, sorry, 5, uh, this will make it 4, 5. And let's say that this one is going to be, let's say 3, 4, 5. You can see that all the parameters are going to be changed. Now let's have a look on these parameters. This will be the feed rate and the rotational feed rate. This is depth of the cut. Well, actually, I should expand this one a little bit. Okay, we have the tool life formula, or the Taylor equation. Just to release that because actually we have here, this should be n, and the value for the parameter itself is given here. This will be the case number 1n, and this is the case number 1c, as you can see here. This is the case number 2c and the case number 2n. Okay, so just use that away from this part. The machine labor rate, the overhead rate as a percentage, the grinding labor rate, and the loading and the unloading time, the tool cost. This is for the high-speed steel, and this is for the carbide insert. The tool changing time is going to be the same for both. The grinding, the ground number. We have 7 for the high-speed steel, 0 for the carbide insert. The grinding time is going to be 5.75 minutes per edge, and we don't have any grinding time for the carbide insert. Now, for the calculation, you need to use the following equations. First, you need to find the value for the CO, then the value for the CT. Okay, now the value for the CO is going to be the same if we're going to use the carbide insert or the high-speed steel. The cost for the tool per edge for the carbide insert is going to be just the cost divided by the number of the edges. While in the case of the high-speed steel, is going to be the price of the or the cost of the tool divided by the number of the useful edges. Okay, now go back to the previous example and you will know what will be the total number of the useful edges we had. This is the grinding available number. Time for the grinding multiplied by the grinding cost plus the overhead cost divided by 60. This is only going to be available in the case of the high-speed steel because we don't grind the tool for the carbide insert. After you finding these two values, you can simply find the T minimum, the V minimum, the TAC for the minimum speed, the CU according to the minimum TAC, and the TU value. Of course, you need to find the total. TU must be multiplied by the patch number, which is the load number here, to find the total time for the operation. Same thing for the maximum speed. Now we are going to go back to the question and let's try to I will do the sorting based on the 9, uh, 8, 9, and the 7, 8, 9 because that's the example we have. I don't know if there's a lucky person who's going to have the same parameters. Anyway, that's what we have now, and that's what I'm going to use in my calculations. Now we go to the question once again. We find all the, well, we know all the parameters, and again to use these values to find the optimum tool life and the optimum cutting speed to minimize the cost per piece, the production rate and the minimum cost creations, and the optimum tool life and the optimum cutting speed to maximize production rate, and finally the production rate for the maximum production rate creations. So I'm going to use a paper and pen to do these answers, and sorry, this will take quite a long time. However, this will be for your own benefit. So we start first with finding the value for the CO, and then the CT, and then after. Oh, I only get to do it for the high speed steel, and you need to do it for the carbon insert yourself. So I'm going to start first with finding the value for the CO. So the CO is equal to the labor cost, okay, plus the overhead cost, and divide that by 60 to find how many dollars per minute. Now, to make that very easy, you remember that in the parameters we have that the labor cost was equal to, just let me change the Excel sheet here. The labor cost was equal to $29. $29. Okay. Now we have labor cost plus the overhead cost percentage, which is 69, which is 69%, 0.69, and divide that by 60. Now you tell me, okay, now what I have done. 29 plus 69% of the 29. That's what I've done here, but I just made it in an easy way. Or at least that's what I like. You are not forced to do that. So if I get to do the calculation for this one, we're going to get the answers to be zero point 0.8, approximately $0.82 per minute. Okay. So we got the value for the CO. Next step is going to find the CT for the high-speed steel cutting tool. First is going to be the cost of the tool. Sorry, because actually I can see that the things is got in blur and that compact because I'm using the phone as an overhead. Cost of tool divided by the useful edges number plus the grinding time, okay, grinding time multiplied by the grinding cost plus overhead. And this all going to be divided by 60. Now we're going to do the same thing. So the cost of the cutting tool we have here was $49. The tool can be grinded for 7 times before it's going to be thrown. So we're going to have 1 plus 7. Now we have one fresh edge in the cutting tool when you buy it, and you can grind for 7 times. Okay, so that's what we have here as an A. Actually, everybody is going to have the same number. Plus, we have the grinding time was given as 7.95 minutes, 7.95 minutes, and multiplied by the grinding cost was equal to um, $34. And this will be multiplied by 1 plus 0.69. Okay, and then divided by 60. By doing the calculation, we are going to find that the number I got is going to be $13.74 per H. Okay, now that's the value for the CO and the CT, and then we can start to apply the equations to find the value for the T minimum first, and then the V minimum, and then the T maximum and the V maximum. And after that, we're going to continue finding the other parameters. So we will start first with the finding the value for the uh, T minimum. So the T minimum, after I find out the CO and the CT, the T minimum is going to be equal to, open the bracket, 1 over n. So the n is actually going to be equal to, just let me check that on the Excel sheet, 0.48 in the case of the high-speed steel. Once again, I only need to go for the high-speed steel. Minus 1 multiplied by the CO multiplied by the T, D plus the CT divided by the CO, and then close the bracket. So if I get to substitute these values, I'm going to have the 1 over 0.44 minus 1. That's what we have in the first bracket. And the second one is going to be the CO, which is 0.82, multiplied by the value of the TD. Now the TD, which is the time, the TD was equal to the time to change the cutting edge was 3 minutes. So I'm going to multiply that by 3 minutes. And then plus the CT, which is the 13.74 dollars per edge, and divide that by the CO value, which is 0.82. Close the bracket, and this will be equal to the 21.47. Okay, that's in minutes. Now, this true life is going to be achieved if I can use the minimum cutting speed. So what will be the minimum cutting speed, the minimum? I'm going to rearrange Taylor equation to C divided by the T minimum up to power n. So the C value we got in this first case was 118 for me, and divided by the T minimum, which is 21.47, up to power the value of the, sorry, 0.48, was 0.44. Okay, and this will give me that the B minimum in that case is going to be equal to 27 point, let's say 27.08, okay, meter per minute. Now we find the value for the V minimum according to T minimum required. We can do the same thing with the value for the V maximum. I only going to do the minimum one, which is almost quarter of the question. But I'm going to continue with all the requirements to find the final solution. So in that case, we need to find the value for the TAC, which is going to be equal to the pi multiplied by the length of the cutting, multiplied by the diameter, and then divided by 1000, multiplied by the V minimum, okay, and multiplied by the feet rate. So pi multiplied by the length, and pi length was 489 multiplied by the diameter, which is 63 millimeters, divided by 1000, multiplied by the V minimum, 27.08, multiplied by the feed rate, which was 1.34. And my answer is going to be, actually, I gave you my answer because I have my own calculator and all the figures given to me. This will be 2.67 is the value for the TAC. Of course, this will be in minutes. Okay, now just do a review before we can go further. So we find the CO, we found the CT, then calculate the T minimum, the V minimum, the TAC according to the V minimum. Next step is I need to find the value for the CU. CU. Oh, by the way, as I told you that in the Excel sheet I shared with you, all these equations are actually typed, so you just simply can copy it and paste it in your paper. But I don't want you just give me the answer. I would like you to give me the parameters of the equation to be typed in. Well, I give you the equation printed, so just replace the letters with numbers. Okay, so this will make your life easier. And wait a second, I think that waiting for the connection. What's happening to the connection? Just give me 1 second. The cat is sleeping. Yeah, now it's working. Okay, so now we are going to go for the CU. The CU equation is the CO multi CO multiplied by the TC, which is sorry, the TL, the loading and unloading time, plus the CO multiplied by the TC. You see that the one we just calculated, and plus the CO multiplied by the uh, tool changing time multiplied by the TAC divided by the tool life. Of course, this will be T minimum. And finally, plus the CT multiplied by the TAC divided by the T minimum. So this will give me the time required to make, sorry, the cost required to make one piece by using the minimum machine time. The tool life at the minimum speed. So the CO is 0.84, 0.82, sorry, 0.82, multiplied by the loading time was the loading time. Just let me find that. Sorry, I think it was. I don't have to look at the question. The loading and unloading time. Yeah, 2 plus 2 divided by 10. So I should have it somewhere in the calculator. Um, to actual cutting. Sorry for that. The loading and unloading time. Oh yeah, excuse me, 2.78. 2.78. Okay, so I will multiply that by the 2.78 minutes plus the CO, which is 0.82, multiplied by this time 2.67, plus the 0.82. Sorry, the writing is not that neat, but actually is much better than what the sum of the student actually submitted as the assignment. Sorry for that. And I know this is actually a mini joke, but anyway, the TAC, which is the 2.67 divided by the minimum to life, which was 21.47. And then we're going to add the other part, which is going to be the CT, which is for 13.4.74, and multiply by 2.67 divided by 21.47. And then the answer for the CU, according to my calculator, is going to be equal to 6.4, or let's say 6.47 dollars per piece. Okay. Now we need to find the value for the GU. the time required to manufacture one piece. The TU is going to be equal. Sorry, the TU is going to be equal to the TL, the time for the loading and unloading, plus the TC, which is the time of the machining. Okay, and actually we can, well, we already calculated that the pi L D divided by 1000 F, so we don't need to write down that once again. And plus the TC itself, okay, multiplied by the V divided by C up to power 1 over N multiplied by the TD. Okay, now, yep, that's what we need to find. And according to the calculation I had, I got that the answer is going to be 5.82. Uh, let's say, let's be more accurate, 5.83 minute per piece is the time required to manufacture one piece. Finally, to find the time of the production of the total load, time total is going to be equal to TU multiplied by the Q value. And according to my Q value, I will get the answers to be equal to 12,468.6 minutes to manufacture the whole batch. Okay, so what you need to do next is calculate the T maximum in the first step. V maximum, TAC according to the V maximum, the CU by using the parameters we got for the T maximum, okay, and then the TU, and finally the T total. You will have two numbers here. After you do that, you need to calculate the CT once again based on the carbide insert. And when you get this value, you can, okay, you can see if, I don't know if you can see me here. Yep, and later you can actually find the value for the same parameters, okay, using find the maximum cutting speed, as I told you first, and then you can repeat the same process by using carbide insert, and then you can find, actually, you can make a comparison between the value we have. Definitely what we can find is that the cutting speed available for the carbon insert is going to be much faster than the one we had for uh, the high-speed steel. The other thing, of course, then that's mean that the tool life also is going to be longer in the minimum speed. What we can also estimate is that the high-speed steel can be grinded from multiple times, so we can have more useful edges for the same cutting tool. While for the carbon insert, if you can have 4 edges, that's what you're going to be limited to, 4 edges, and that's it. You need to throw it out and get the new cutting tool. So I would like to try very quick comparison between what we have in two cases, and that's it. That's what you need to do. I can guarantee that you can do this uh, assignment in something like 30 minutes and submit it. Just try to get rid of it. Now you have all the answers. If you would like to have another tutorial, I can make a live one and we can sit together and make a discussion about the steps of the solution. And if you have any abstract on, make you finishing this assignment as soon as you can. So don't leave it for the late time because we're going to be busy with the major projects we have now. 45 marks. This one is 10 marks. We're going to have 45 marks of floating somewhere. And the first one is the reverse manufacturing, and the other one is going to be the major project, which I'm going to make a video for it by tomorrow, hopefully. Actually, I have some samples available for me. And let me show you some of the samples we have here. But I don't want you actually to mix between both now. We can always come to it later and see what the other people does, and also again to I cannot, I don't know why. Okay. And we will be able actually to overcome this one. Next week, I'm going to, exactly, I'm going to hire someone who's going to help you with the MATLAB image processing. And before that, I'm going to send you some. I will ask him to send you some examples, and you can actually try to apply these examples yourself. So when you come to his session, you have to be able to ask him a question. Just remember again to hire him once and only once. So if you miss that, there will be no one to be asked about these things. You have to learn yourself. Thank you very much, and hope to see you soon.